Okay, today a few more details on enthalpy, and we've investigated chemical reactions in terms of enthalpy of reaction. We've used some factor label. Well, now let's look at how the bonds actually impact the delta H for the reaction. So there's definitely energy involved with the bonding of two atoms together to make a, well, sometimes a molecule, but at least a bond between two atoms. That might be inside of a bigger molecule. And some of you are going to memorize this. I don't recommend that idea, but if you wanted to figure out the delta H for the reaction, if you looked at all the bonds broken and then all the bonds formed, subtract the two from each other, that would get you the delta H for the reaction. Now, what I would rather you think about is that if you want to break a bond, and you could try this with a pencil. I know, no, pencil's not a bond, but it would work the same way. If you want to break a pencil, that pencil has to absorb energy. If you want to break a bond, that has to absorb energy. Absorbing energy is a positive value. So that's why there is a lack of a negative in that area there. So all the bonds broken, positive answers. Let me erase all these things because they're getting a little busy here. So there's really a positive there. And then there is a negative for all the bonds formed. So anytime a bond is formed, energy is released. And so then if you sum that, add all those up, I guess, then you're going to get the delta H for the reaction. I think we've already talked about this when we were talking about bonding earlier in the year, but the more electrons involved with that, the more energy associated with that bond. So triple bonds typically have more energy than a double bond. Double bonds typically have more energy than a single bond. And by the way, all these ideas are all averages. Okay, not specific to one particular bond, but all the nitrogen to nitrogen bond, single bond, or how nitrogen to nitrogen triple bond, or whatever else you wanted to discuss. And then also the lengths are related to all this too. So the bond length for a single bond is going to be the greatest. Triple bond is going to be the least. So really, the more energy involved with the bond, the shorter the distance between those two atoms. Okay, so again, I was recommending that you guys understand that broken absorbs energy, formed releases energy. So let's jump in here. So we have, this is a table that would be in any textbook. Probably a bigger table would be in the textbook. If you had a test question, I would give you what you need to be able to answer the question correctly, and probably more information than is provided. But what's not given to you is the chemical reaction and also the Lewis dot structures. And without those two things, it's going to be impossible to answer these questions. Okay, so let's just kind of go back and look and make sure that what we were talking about in that last slide makes sense. So here are three different types of bonds: single bond to carbon, double bond to carbon, triple bond to carbon. And you can see that the triple bond to carbon has 812 kilojoules per mole. Again, these are averages. The double bond carbon 620, and the single 347. So that does match up with what our ideas were. It says use bond energies to estimate the enthalpy of formation for N2H4. So to be able to do that, we definitely have lots to be able to, that we need to do first. So formation of N2H4. So there's N2H4. Well, it's from its elementals. Any of these formations are from its elementals. So that must be nitrogen gas and hydrogen gas. And that's going to require 2 hydrogen gases for every 1 nitrogen gas. So there's our chemical reaction. But we need more than that. So what is nitrogen to nitrogen? Well, you have to know, and this is going back to Lewis dot structures, how to formulate single, triple bonds, a single, double, or triple bonds. And then the hydrogen is going to be that. And then N2H4 is going to be that. Okay, so now we have all the information to be able to get this question correct. So we have an N triple bond to N, so that's 941. I'm not going to put kilojoules per mole. Everything in here is going to be kilojoules per mole. We have 2 H to H's, that's 436.4. Then all of our bonds formed are all going to have negative values. And you can't lose count of these. We have 1, 2, 3, 4 of the HN or NH bonds. So we had 4 of those, and they each them have 393 kilojoules per mole. And then we had 1 N single bond to N, and that's 193. Okay. I'll let you do all the addition, subtraction, so we can kind of move through this a little quicker, but that's the work. Remember that bonds formed all negative values, and so that's why I have that negative right there. So everything to the right of that negative is bonds formed, and then everything to the left of that negative is all bonds broken, and those are all positive values. That's the easiest part to screw up. Second easiest part to screw up is not having your balanced chemical equation. And then the third thing to screw up would be not knowing how to do your Lewis dot structures. Or I guess the accounting of how many bonds that you have. Did you count all the bonds in the chemical reaction? So the next one, almost the exact same question. We just have a different chemical reaction. So what we got this time? We have H2. And we have, in case you don't remember the name of that, ethine, and that makes ethane. So what do we got here? We have, well, is that balanced first? I don't think so. I think we're going to need a 2 there. So we have an H to an H. We have another H to an H. Let's kind of separate this. We have and an ine, that's a triple bond. And then anes are single bonds. Now here's an interesting item for this question, is if you have somewhere on the left and somewhere on the right of the arrow identical types of bonds, then you don't have to count them, because the H to C here and the H to C here will cancel out with 2 of those H to C's. If you wanted to count them on both sides, that's okay too. You don't have to. And I think that's the only thing that's going to add up equally like that on both sides. So we have, looks like we have 2 of those. You know, let's change that again. Let's go to blue. So we have 2 times 436.4. We didn't count this C triple bond C, so that's 812. And then all our bonds formed. I think we have 1, 2, 3, 4 of those CH bonds. And I think we have 1 of the C single bond C, and that's 347. Okay, so again, we have the negative in there because bonds formed, release energy. And then over on this side, we have a positive. I know I didn't write that down. You don't need to. And those are all energy absorbed because those are bonds broken. So you add them up, and that's going to be your answer. I think we've had these kind of questions before, and certainly we have now data that will back us up with this, but we'll try to go without that. Increasing bond length, so shortest middle and longest. So I guess we should maybe do that. Whoops. Now to do this one, I think you'd probably go back and look at the numbers. So you want the highest delta H going down to the lowest delta H, or bond enthalpy, I should say. Okay, so whatever number is the highest, that's going to be your smallest bond or shortest bond length. So here's an AP question. This was part of an AP question. So they were nice enough to already give you the Lewis dot structures of those two chemicals. And it's saying determine the delta H for the reaction of HCNO, that is this chemical over here, and it's going to go to that chemical over there. There's no bonds that are identical on both sides of the arrow, so we can't cross anything out. You just now have to add everything up. So we have an H to C. So I'm going to write it up top here. We got 413. We have a C triple bond N. That's 891. We have an N to an O. That's 201. So those are all positive values. Then we have negative values. H to N, that's 391. We have an N double bond to C, that's 615. And C double bond to O, that's 745. So you add them up. There's probably work here. There we go. So there's our answer. So when we add all that up, we get a negative value. Question 3 of 3 for release bond enthalpies. We've talked about this before. We've never seen a drawing of this, but up here, that's an ionic compound. And the ionic compound has to break up into ions. Break bonds. Breaking bonds is endothermic. It has to absorb energy. The next thing we have is water. Now, how do I know all this is happening? Because I've previously read those 5 lines of words that you guys can read on your own. But step 2 is water. And the water has to break the hydrogen bonds that take place between water molecules so that they can have these empty spaces to accommodate the ions that are going to fill up those spots. So breaking hydrogen bonds is going to be another endothermic process. When you take the cations and anions and you have them attracted to the polar nature of water, the negative, partial negative end of oxygen of water, and the partial positive end, hydrogen end of water, those are bonds formed. And so that's going to be an exothermic process. So we need to find an answer that's going to match up with all those. Endo for 1, endo for 2. That looks like we got D. Looks like D is going to be our only answer, and I bet I probably have all the answers right below. Yeah, I do. So we were wrong with that one. I think the second one is a little interesting here. So we have a chemical reaction. So if you just look at that chemical reaction, it may be tough to visualize. So I'm going to write the molecules down here. So here is a hydrogen peroxide, but there's 2 hydrogen peroxides. And that goes to 2 waters. And a oxygen gas. Okay, so let's do this first. Is there anything that is the same on both sides? We have 1, 2, 3, 4 HO or OH bonds. 1, 2, 3, 4 of those on that side. So the OH bonds have nothing to do with this question. So ultimately, what we really have going on here, as far as differences of bond enthalpies, is we have an O single bond to an O and another O single bond to an O, and that's going to get us over to a O double bonded to an O. Now, it's not the total chemical reaction, but this is the only thing that changes as far as bond enthalpies. So we have a whole answer. So we've been, with these previous questions, trying to answer what's the delta H. Well, this time the delta H is given to us, but the parts aren't given to us. So assume that the bond enthalpies of the oxygen hydrogen bonds in H2O are not significantly different from those in H2O2. I had already assumed that. Based on the value of delta H for the reaction. By the way, we don't like negative 196 because this is a multiple choice question. You don't get to use a calculator on this. So it might be easier to think of this as negative 200. It's not really much different from negative 200. So let's try that. Which of the following could be the bond enthalpies for the bonds broken and bonds formed? So remember that these are going to be positive values and these are going to be negative values. So I guess we could do a process elimination. The O's, I'm looking at answer A here. So 300 plus 300 minus 500. Does that get you negative 200? No. I think it gives you positive 100. So let's look at B. 150 plus 150 minus 500. I think, bingo, that gives you negative 200. There we go. And the rest of this is just a little bit review of how scientists had already figured out these average bond enthalpies, along with distance, internuclear distance. Okay, so again, spectroscopy is definitely a good instrument for understanding lots of things. In this case, I think we'd have to use, in this kind of range, probably the vibrational. I think we've talked about this graph before, but let's revisit this again. We love this sweet spot. So the nuclei of two atoms are in the sweet spot of attracting each other and repelling each other perfectly. Bond has formed. So they've remember, when you form bond, you release energy. That's why the potential energy is at its lowest point when the bond forms. We don't really like up here. They're too close together. They repel. They're too far apart in this little area here, but they reach that sweet spot. So if you can look at how far it is down on the y-axis, that can kind of give you an indication of the amount of energy associated with the bond. And if you look at the distance on the x-axis, that kind of gives you an indication of the size of those atoms that are in that bond. I guess it also can give you indication of single, double, and triple too. A couple questions that go with this. These are kind of very typical questions. Potential energy of the system of two atoms is a function. Okay, we already know all that. Which of the following is true regarding the forces between the atoms when their internuclear distance is x? So here is our x, and we love that sweet spot. That means the bond has formed. There's probably an answer. Well, let's look. We already have the answers. Answer A. Attractive and repulsive forces are balanced. Up here, if you remember, they're repelling each other. Way out here, they're too far apart to attract, but it's about attracting. So this is in perfect internuclear distance from each other, where the repulsive and attractive forces are balanced there. So that matches up perfect with our graph with the answer A. What's going on here? So now we have three different molecules, X2, Y2, and Z2. Let's investigate this. So Y2 goes the furthest down on the Y-axis. Therefore, it's going to have to be, in my opinion, the shortest bond. Well, let's not talk about the shortest bond, because that's not going to help us out when we don't know what these X's and Y's and Z's are yet. But it's definitely going to have the most energy associated with it. So that's typically a triple bond. Looks like the molecules in question are that, and that. So because this one dips down so much, I gotta believe that is N2. So Y2 is really N2. Oh, we already got an answer there. We already know it's A just by that alone. That doesn't always happen, but let's try to go just to investigate a little further here. How do we know then that X2 is really H2? So we've already identified this one. So how do we know that X2 is really H2? Well, let's look at how far away these are from each other. So X2, yes, H2, is not as far on the x-axis as O2, and that would make sense. H, the atom H, is the smallest atom, so that's going to be a very, very, very small. Even though double bonds are typically smaller than single bonds, H is so much smaller than O. I think that's going to give us that indication there of why we like X2 as H2. But it turned out we didn't need that information anyhow, because we've already identified it, because N2 was that triple bond. Okay, that concludes today.